Oh, yeah, this will be handy. Okay, so my name is Ken Jung, and I work at the School of Medicine. And a lot of our work focuses on very practical problems. And unlike the talks that you've heard already, in which the obstacles that you're trying to overcome with your training are fundamental, intrinsic obstacles that arise from the structure of directed graphs or the physics of turbulent flow, a lot of the problems that we have to overcome have to do with very man-made processes, i.e. how we've organized and paid for clinical medicine in the United States. And I'm going to be very upfront with my agenda for the talk. Really, the way that I want to approach this talk is as a recruiting talk for the ICME students. And who are the ICME students? Like, who's a student right now? Okay, so we happen to have like the good fortune of working with Sebastian Dubois, who just graduated from ICME last winter quarter. And we were so incredibly happy with the work that he did for us that we decided that we wanted to see if we could convince any other ICME students to come work and help us solve some of our problems too. Okay, so that's the upfront, hopefully completely transparent agenda here. And in order to convince you that this might be an interesting area to spend some of your effort, your hard-earned and your valuable time as students at Stanford, I'm basically going to tell you about an arc of work that we started with Sebastian a little over a year ago. And it's going to start with a very specific clinical problem, and then it's going to branch out into something that's a little more general, but is nevertheless very motivated by the specific problem that Sebastian originally started working on. Okay, so the context is there's a genetic disorder called familial hypercholesterolemia, and I'm going to say FH because I don't think I can get that out without blundering over it again. So it's a genetic disorder. It's usually, I think, linked to mutations in about one of maybe 3 different genes. And it basically causes a buildup at a very young age of low-density lipoproteins, or it's also called the bad cholesterol. There's, I guess also the good cholesterol. And this happens in people while they're relatively young, in their 20s and 30s. And so the way this often presents is somebody who seems to be in the prime of health in the 20s or 30s will suddenly show up in the ER with all the signs of having a heart attack or coronary artery disease that's more typical of somebody in their 60s who's, lived a pretty indulgent life, I guess. And it turns out that the population prevalence of this, depending on the population, is anywhere from, say, 1 in 250 people to 1 in, say, 400 people. So 1 in a few hundred people in the overall population. But the kicker is that this is incredibly underdiagnosed. It's only about 90% of the cases are estimated to be completely undiagnosed right now. And for reasons that have to do with the cost structure of identifying these patients, it'd be great to have a way of identifying these patients relatively cheaply. Right now, the most reliable way of identifying these patients is through a genetic test that costs on the order of, say, $300 a person. In a typical lipid clinic or cardiovascular clinic, as in Stanford, you could estimate that, for round numbers, let's say that about 1 in 100 patients in the clinic has FH. Now, if you go through the numbers, and it turns out that one of the most effective treatments for FH and managing FH so that you can go from your 20s to live to a ripe old age are a new class of statins or cholesterol-controlling drugs called PCSK9 inhibitors. And I'm just going to call them the new generation statins because, again, that's easier. They cost around $10,000 per year, kind of conservatively, possibly more, possibly less. Again, in the US, it depends on the negotiations between payers and insurance companies. So if you run through all of that, you can estimate that it's going to cost roughly somewhere on the order of $30,000 to $40,000 to identify that one patient who can benefit from this drug, very expensive drug. And most of the cost is concentrated, in fact, on just identifying who that patient is. Okay, so if we had a classifier or something that could operate on reasonably available data that you could just run, and presumably the classifier doesn't take too much energy to do the calculations, and you can get, let's say, a positive predictive value for about 50%, then all of a sudden that really changes the balance of where the cost is going. It's going almost entirely towards treating the patients that you've identified. So that's a very desirable thing. And of course, one of the most readily available sources of data, did we ever find, did this ever work? Okay. Never mind. Okay, so I'm going to proceed without the slides. So one of the most readily available sources of data that we have about patients are in these things called electronic health records. Okay, so when you go to the Stanford Hospital, you're going to get all sorts of measurements taken and lab tests done, and the doctors and nurses who see you are going to write up their notes, and that's all of that data is going to go into an electronic health record system. That's been going on at Stanford for a couple of decades now, and I think at this point in the United States, there's roughly maybe 70 to 80% adoption of this sort of system, at least in hospitals, and it's a little slower in primary, outside small practices. But anyway, so this is a great source of data. It has its pitfalls because this is all human generated, and of course, anytime you have humans generating data, it has all sorts of weird biases that get introduced by the data generating process. But at Stanford Hospital, we've accumulated at this point data structured as in diagnosis or discrete diagnosis and medication codes, and unstructured in the form of the free text of clinical notes. We have data for about a little over 2 million patients, roughly 40 million notes and roughly 40 million structured discrete diagnoses, et cetera. And it'd be great if we could use some of this data. And it sounds, at first glance, as if, okay, this is, I don't know, this sounds kind of dodgy because we've got, what, 2 million patients. The space of possible codes is actually frustratingly high. It's on the order of, let's say, a couple of million things. But it's a very long tail, as you might expect, and you can throw most of those things out. And things start to look pretty good. Again, you've got 2 million patients and roughly, let's say, 100,000 inputs. Seems like you're good to go. But here's the kicker, and there's always a kicker when you're trying to do something in clinical medicine.
Ken's up there, by the way.
Ah, okay, great. I'm just going to keep going. Okay. Okay, well, I'll show you pictures of Sebastian and Nathaniel at the end. Okay, so you've got this incredibly large data set. It's actually not that large by modern standards, but here's the kicker. How many cases, reliable labels, do we have of patients with FH? Turns out that when the people at the cardiovascular clinic at Stanford came to us with this problem, they had 93. Okay, 93 patients, roughly 100,000 inputs, and that's if you flatten things over the longitudinal time series. Not so good anymore. So Sebastian's first take at this problem was to essentially take, and here I think actually seeing something will help. If I can, okay. Yeah, okay, so I'm just going to keep winging it. So the current state of the art for identifying patients with FH is basically there's a list of questions. You answer yes to the question, you get a certain number of points. You answer no, you get 0. And you answer all the questions, usually by reading through a patient's charts or clinical notes, and then the number at the end gets binned into some categories that are either high risk, low risk, et cetera. Okay, so it's pretty primitive, it's incredibly labor intensive, and it's still not definitive. The definitive test is actually doing the genetic test. Okay, we end up with 93 examples of such patients who have been definitively diagnosed. Sebastian's first take on this was essentially to figure out, okay, I've got all these questions in this questionnaire. It's not in a computable format, so I'm going to basically make it computable, estimate the answers based on the data in the EHR, and then just fit a simple linear model based on, instead of hundreds of thousands of features, 20 features that are all computed more or less elaborately from the EHR data. Okay, and that's a lot more manageable. It's not ideal because, of course, we'd still like a lot more information than that. But it's probably, it turns out, it was close enough to get us in the ballpark of where it was actually practical and cost-effective for all the parties involved, the payers and the drug companies and everyone else, to say, that's interesting. I think we can sort of work with this and maybe apply this at a population level across the United States, assuming that a model like this actually generalizes. Okay, so at this point, Nathaniel and Sebastian started working together. Nathaniel was another grad student here at Stanford who also recently graduated in MS&E. And they got interested in the question of how to generalize this so that you could do, basically, when you're in situations, as you very often are in clinical medicine, where you want to build a classifier of some sort, but you have just a handful on the order of, say, 100 or 200 confident labels that are usually generated by doctors reading through charts. That's why it's expensive. Not so amenable to Mechanical Turk. What do you do in those situations? And in computer vision, like, there's a pretty clear answer to this sort of thing. In computer vision, what you do is you would take some large neural net that was trained to do object recognition on ImageNet. And basically, you would take that and use that as a starting point for your actual problem that you're interested in, where you've got a much smaller data set. Okay, and generally that paradigm of learning a model or learning how to represent something, some domain, using a very large data set where you've got easy, and readily available labels, and applying that to another problem where labels are a lot more costly and harder to come by. That's just called transfer learning or domain adaptation, et cetera. So they got interested in the problem of how to accomplish this using the notes, clinical notes. And clinical notes are strange beasts. It's not like Wall Street Journal text. It's very idiosyncratic. In fact, if you gave me 2 clinical notes from 2 different institutions, you could probably, okay, not even me, but any of you could probably tell, oh yeah, these probably came from different places because the way they're formatted, the order in which they talk about things, et cetera, is just different. And so it's not an easy problem. It's also compounded by the fact that mostly in NLP these days, including the deep variety, people are often modeling things at a character level when they're working with very large data sets and complicated, basically they're doing addressing problems which are foundational in natural language processing and in certain problem domains such as dialogue generation. But for us, they're a little bit irrelevant. And so they got interested in ways that they could leverage some of the advances in deep learning. And I hate to bring that into things because it's a little bit overhyped. But anyway, there it is. OK, there's your obligatory deep learning thing. They got interested in whether or not they could leverage some of those advances to basically come up with a way of extracting or summarizing a history of clinical notes for a patient such that they could, with a very small number, like down to n equals, say, 100 or 125, predict with reasonable accuracy events that were going to happen in the future. And we don't mean like simple events like, hypertension, because if you have once you have hypertension, you probably have it. It's a persistent thing. But we mean like rather more complex things like, is this person going to show up in the ER in the next 6 months? Is this person going to be admitted as an inpatient? Or are they going to die? Okay. And it turns out that they could do surprisingly well against some pretty strong baseline methods. And I'm going to leave it at that. For the students here, if you'd like to hear more about exactly what they did, then please get in touch with us. We'd love to have some more really bright, motivated ICME students work on problems like this with us. Okay, thank you.